Afternoon, to the afternoon part. So the first speaker in the afternoon is Olivier Debarre from the École Normale Supérieure, and he's going to speak about Fano varieties and EPW sextics.
Thank you very much, and thank you very much to the organizers for inviting me here. So I had planned to begin this talk by recalling some facts on cubic hypersurfaces, but so my task has been made easier by the previous speakers who already mentioned more or less all that I wanted to mention. So let me just briefly recall some facts. About cubic hypersurfaces. And so the reason I'm doing that is that the varieties I want to study, I want to study them along the same plan as the properties that I mentioned here. So maybe I should say that this is joint work with Sasha Kuznetsov. Okay, who will be the second speaker this afternoon. Okay, so first of all, let's consider a smooth cubic threefold. So as was already mentioned, its Hodge structure is such that we can define an intermediate Jacobian. So this is the intermediate Jacobian. And it turns out to be a principally polarized abelian variety. So let me choose a theta divisor, PPAV, for principally polarized abelian variety of dimension 5. And the fact that, actually, as Chelsov already explained this morning, this can be obtained as a prime variety, and that makes the study of the singularities of theta quite easy. And one can show that theta has a unique singular point. And this implies immediately that it's not J of x is not a Jacobian, and there's no Jacobian factor. And so this implies by the criterion that was explained this morning that x is non-rational. And moreover, one can show, I think this is in a paper by Beauville, that the tangent cone, if you look at the tangent cone to theta at this singular point, let's call it O, and you take its projectivization, then this is naturally isomorphic to x. So in particular, this implies a Torelli problem. Torelli property, meaning that x is uniquely determined by its intermediate Jacobian. So another way to phrase that is that you can consider a period map going, say, from the moduli space of smooth cubic threefold. So this is a coarse moduli space which can be constructed by standard GIT methods. It's an affine space which is 10-dimensional. So 10-dimensional GIT moduli space. And taking a cubic threefold to its Jacobian defines a period map, which is an open embedding. Okay, so here is A5, the moduli space of 5-dimensional principally polarized abelian varieties. Okay, so the prime is that, so this is 10-dimensional, this is much bigger, and so there's, I mean, one can study the image in this space, but it's another way to look at this is to construct another period map. So which goes like this. So it starts from the same moduli space, M. It goes into a period domain, which I won't be more precise about. And this is done by not looking at the Hodge structure of X, but looking at, so this is obtained, I'll be vague here, obtained by considering the Hot structure of a triple cyclic cover of P4 ramified or branched. Okay, so this is 3 to 1. This is a cyclic cover branch along X. And so this gives a very nice map in the sense that this is 10-dimensional, but this is also 10-dimensional. So this map has been studied by many people, including Radu Lazar, who's here, Jim Carlson, and some other people I don't remember. So anyway, so this is an open embedding. And so both sides can be compactified in a certain way so that it becomes sort of an isomorphism. So this is very nice.
Hodge numbers of X tilde?
So it's not it's a piece of the Hot structure of X tilde, so you have an automorphism of all the three.
Oh, but it has an action of
You have a cis reaction, and you take one part, one eigen. You have this world specialist here. Okay, so what about now cubic fourfolds? Okay, so what do I want to say now? So the Hot structure now is of on H row of X is of K3 type. So we can define a period map again. So this will be same notation, smooth cubic fourfolds. So again, this is obtained by a GIT construction, and this is 20-dimensional. And the period map goes to a period domain, which is also 20-dimensional. So this, the fact that, as I indicated here, this map is injective is the Torelli property, which was proved by Voisin in a thesis. And again, this map has been compactified. Again, I should compactification studied by Radu. Okay. So the GIT construction provides you with a compactification, but you have to identify the semi-stable points and the right thing. So it's a bit complicated, and of course I won't go into that here. So I should mention, it was already mentioned in the previous talks that associated with X there is the variety of lines, which is an important tool, which was used a lot by Voisin in her proof. So this is the variety of lines in X. So it's a subscheme of the Grassmannian of lines in P5. And so this was shown by Beauville and Donaghy to be a smooth, I mean smooth is easy, irreducible holomorphic symplectic fourfold. I think it was mentioned by Yuri this morning, and which is a deformation of the Hilbert scheme of pair of points on a K3 surface. And so why is this variety important? Well, it's because so Beauville and Donaghy also prove that there is an isomorphism between the primitive part of the middle cohomology of X. So this 0 here indicates a primitive part, which I don't want to define here. So this is a lattice for the intersection form. And there's the incidence correspondence gives you a natural correspondence, a natural map here between the H4 of X and the H2 of f of X. Okay, so this is given by incidence. So here, this is the lattice endowed with the Beauville-Bogomolov quadratic form, which was mentioned by Chinkel this morning. Okay, and this is an isometry. So here I need to also put primitive part here. So in some sense, you can look at, you can complete the diagram above by, so M is still our moduli space of cubic 4-fours. I can associate to X this f of X. So this would be a moduli space of irreducible holomorphic symplectic 4-fours with a certain type of polarization. And this isomorphism here tells you that our original period map factors through this new moduli space. Okay, so this is easy to show that this is injective, and this is also injective by Verbitsky theorem. There's a Y somewhere, right? Good. Okay, so this gives you a new proof of Torelli. Okay, so I guess, oh, yeah, okay, so maybe also the last point I should mention without more details is, of course, probably the most important question about this smooth cubic 4-fours is the rationality problem. So as you know, and that was, as it was already mentioned, some rational examples are known, but no irrational smooth examples are known. Okay. So this is all that I wanted to say about cubic hypersurfaces, and now I want to define and study another class of varieties, which are obtained as follows. So let's say we call them GM varieties, which is for Gushel-Mukai varieties. So they are defined as follows. So the definition is a little bit, you may wonder why we are interested in those varieties, but that's, maybe it's a good question, but I'll let you judge of that at the end of the talk. So I define it this way. So we take the Grassmannian of two planes in a 5-dimensional vector space. So my running notation is that whenever I have a vector space for which I want to indicate the dimension, it will be the index. And so I intersect it with a linear space and with a quadric. So all of this takes place in the Plucker vector space. And so if the intersection is dimensionally proper, this will be of dimension n. And we assume that it is smooth, which is the case for generic choices. If you compute the canonical class using a junction, you find that it is minus n minus 2 h, where h is the hyperplane class. Okay? So in particular, when n, so n varies between 5, I mean, the highest possible value of n is 5, because this is a 10-dimensional vector space, and this is a subspace. So when n is equal to 3, 4, or 5, this is a Fano variety. Of, so people say of co-index 3. It means of index n minus 2. When n is equal to 2, this is a K3 surface. And when n is equal to 1, this is a curve of genus 6. And I should have mentioned that it has degree 10. So I should mention that in each case here, dimension from 1 to 5, this construction provides an open subset of, let's say, the moduli space of these varieties. Meaning that if you take a Fano variety, for example, of dimension 5, degree 10, dimension 5, degree 10, co-index 3, you have to assume that the Picard group is as rank 1. Then you'll find that you are in this case here, at least in general. So this is the work of Mukai, this classification result, that most varieties with these invariants are constructed like this. For K3 surfaces, for example, you get almost all K3 surfaces of degree 10, and you can identify exactly which are constructed like this. For curves of genus 6, it's the same thing. You obtain all curves which have maximal Clifford index, for example. You can say that. Okay, so I should add that. So the case n is equal to 5. So in that case, you forget about this piece here. These varieties were called quadratic line complexes and were studied by Beniamino Segre at the beginning of the 20th century. So what do we want to do with these varieties? Well, almost all of the points that I mentioned for cubic hypersurfaces, you can ask the same questions here. So so the first one actually was not an issue for cubic hypersurfaces because it's very easy to construct. It's the existence of, let's say, construction of moduli spaces. Okay. It turns out that it's not the standard GIT methods do not work here, so we have to do it another way. I explained how you can construct also, as was the case in here, a symplectic variety, reducible holomorphic symplectic variety. So associated irreducible holomorphic symplectic variety, 4-dimensional also. You can study the period maps. You can study birationalities, rationality question, or and then there's also another last point. Maybe I won't have time to do it, and I'll let Sasha talk about it. There's something, a duality between these varieties here, which I may not have time to explain. Okay, so I'll explain an alternative construction of these varieties which provide an answer to the first question. And this is done via elementary symplectic geometry. So let me call that Lagrangian geometry. Okay, so assume you have a symplectic space, a vector space V, with a non-generate skew symmetric form, and assume also that you have, so this is a symplectic space. Assume that you have a decomposition of V as a direct sum of Lagrangian subspaces. Okay, meaning totally isotropic subspaces of maximal dimensions. Assume that you have a third Lagrangian. So this is sort of fixed. Now I take any other Lagrangian, then this setup here defines a quadratic form on A just by QA of x equals omega of x1, x2, where x1 and x2 are the two projections of x on the factors L1, L2. So this is a quadratic form. And so it defines quadrics. So quadrics, so what I'll call quadrics are not necessarily quadric hypersurfaces. Okay, I just mean subvarieties of a projective space of degree 2. Okay, so the first, so I'll define them like this. So for I is equal to 1 and 2, this will be defined in. So this will be here a quadric hypersurface in this thing here, but I'll look at it as a quadric in PL1, where Wi is the projection of A. Okay, so this is very elementary, and the following lemma is also very elementary. So the lemma goes as follows. These two quadrics here, Q1A in PL1 and Q2A in PL2 are projectively dual, I guess, projectively dual quadrics. So via the duality, so L2 is naturally isomorphic to the dual of L1 via the symplectic form. And these two quadrics, these two dual quadrics determine A. And conversely, let's say you can obtain all dual projective quadrics like that for a suitable choice of A. So, and all pairs of dual quadrics can be obtained in this way, Okay, so as I said, this is very elementary. So we apply this construction, construction, I guess, in the following situation. So start from a six-dimensional vector space and choose a splitting as a direct sum of a five-dimensional and one-dimensional vector space. Okay. And then you look at wedge 3 of V6. And so it has a natural symplectic form defined up to a non-zero multiple. So just defined by the wedge product. So the wedge product lands you in wedge 6 of V6, and you choose an isomorphism with C. And this decomposition gives you decomposition into two Lagrangian subspaces, wedge 3 of V5, which is obviously Lagrangian for the wedge product, and the other piece is wedge 2 of V5, wedge V1. Okay, so this is a notation which is easy to understand, I guess. Okay. So now whenever you have a Lagrangian in wedge 3 of V6, you can perform the constructions which I just explained, and so in particular you obtain a quadrics Q1A and Q2A, which is So Q2A, remember, it's probably still there. It's contained in this. So this is the projection of A onto the second factor. And so this is contained in this. And I can identify this with okay, so now I guess you see where I'm going. Once you have a quadratic hypersurface in a linear subspace in P wedge 2 of V5, we can define an X. Okay, so we set X to be, well, the intersection of this with the Grassmannian. So what does this construction depend on? It depends on the choice of A, of course. But so if you fix this V6 here, it also depends on the choice of the hyperplane. Okay. So this is if this is smooth of the correct dimension, this is one of our variety. If smooth of dimension n. Let's say of expected dimension, because I haven't defined the expected dimension is if you remember, this should be of dimension n plus 5. So this is dimension of V2, W2, sorry, minus 5. Anyway, so this gives you a way of constructing your X, and maybe I'll. So you may think that it is. It sounds much more complicated than the original construction, but the fact is that there is a very surprising criterion that tells you when this happens here. And this is very easy to phrase in terms of A, and it's independent on the choice of V5, which makes the whole thing a very powerful tool. So let's see. Okay, so this is maybe the first main theorem. Let's say we have an isomorphism or a bijection. It should be phrased in terms of isomorphism of between two functors, I guess. But let's be a little vague on this here. So on the one hand, I take A to be Lagrangian. Okay, and so this is the construction here. And I'm leaving some space here, and I choose also a hyperplane V5 in V6. And so the relation of between the dimension of X and the data here is that so the dimension of A intersected with this should be 5 minus n. So this is nothing but the kernel of the second projection of A onto the second factor. So this gives you the dimension of this thing here. And on the other side, you get X to be a GM variety of dimension n. By definition, these varieties need to be smooth. So I'm adding smooth here. And the smoothness corresponds to the fact that A contains no decomposable vector, meaning vectors which look like this. Okay, so no non-zero decomposable vector. This is a necessary and sufficient condition for X to be smooth for all choices of V5. Okay, so in other words, you've reduced the problem of computing isomorphism classes of GM varieties to a problem on the Grassmannian Yeah, on the Lagrangian Grassmannian on wedge 3 of V6.
Like this or only some?
As I define them, yes. Okay, there are some deformations of these which are not, which I don't want to include into the discussion, which actually create a lot of pain. Okay, so why is this easier to construct than this? Well, the thing is that this has already been done by Grady. So constructing the moduli space of Lagrangian here, it's pretty easy. It's just a GIT construction, but this added data here is actually sorry. Yeah, you take the quotient by PG by.
But I was wondering, so in his construction, you don't have the V5 or am I wrong?
Yes, yes. So Grady constructs. Well, let me. I'll just explain here. Okay. So the V5 here satisfies this property. So let's say you fix A at above, meaning without non-zero, with no non-zero decomposable vector. So you want to look at the sets of hyperplanes, so which I view as elements of the dual vector space, such that the dimension of their intersection with A, let's say, is at least K. Okay, let me call that YA at least K. So we defined this. So Grady theorem is the following. So under this hypothesis here, so of course YA 0 is just the whole thing. YA at least 1 is an integral sextic hypersurface. Which he calls EPW sextic for Eisenbud, Popescu, Walter. It's singular locus, singular along as you can expect, the next step in the filtration. This thing here is itself an integral surface. Which is singular along the next step, and this is finite. And this is there is no YA at least 4. Okay, and for A general, let's say to be more precise, outside of a divisor, this is empty. So if you put all that together, you find that there is this allows you to construct a moduli space. So corollary. I should say that this is true only for n at least 3. So n equals 3, 4, 5. where for n equals 2, we're dealing with K3 surfaces, and we don't need to construct a new moduli space. So for n at least 3, there exists a coarse moduli space Mn, a quasi-projective, and a map and a morphism Mn to, let's say, E. So E will be the moduli space of A, or EPW sextic, as you wish, of EPW sextic. And the fibers are the fiber of a given Lagrangian A is isomorphic to, so maybe I should, so this is the part of this filtration here, which corresponds to K is equal to 5 minus n. So maybe I'll just write it this way, I don't know. So I hope it's self-explanatory. So in some sense, so let me maybe draw a picture. So there are two things. You get a precise description of this moduli space, and also you notice that they fit together. So here you have the base space. Here you have a point A. So what you have here is, first of all, you have a P5 bundle. Inside this P5, you have the hypersurface YA, and you have its singular locus. Okay, let's forget about the last piece, which is usually not there. So this is 5-dimensional, the big thing here, 5-dimensional. This is a hypersurface, so it's 4-dimensional. This is two-dimensional. And so this is, in my notation, this is M5, meaning the complement. This is M4, and this is M3. And the dimension of the base is 20. So in particular, you see that some of these moduli spaces contain complete surfaces for M3 and complete curves for M4. And M5 actually can be constructed using GIT, and it's affine. So, okay. So this is the construction of the moduli space. We can ask now about periods. So this is also an interesting question. So there are two cases. Either n is odd. So in our case, it means n is equal to, well, let's forget about curves, 3 or 5. In this case, we have intermediate Jacobian. Jacobian, which is a 10-dimensional principally polarized abelian triad. Or n is even, so 2 or 4. In that case, we have a Hodge structure which is of K3 type. So in the first case, you get a map to the moduli space of 10-dimensional principally polarized abelian varieties. Here you get a map to your period map to your period domain, which is the same type. I mean, it's a same type as the one which I called D earlier. But now we can use the same trick that was used for cubic threefold in the following sense. We can change the dimension. Remember that our varieties are obtained as quadratic sections of something. This something turns out to be automatically smooth.
Okay, you mean just the 3-1 number 1, or also the rank is...
The rank is the same, yeah. I mean, you'll see later, yeah. It's the same as the period domain for irreducible holomorphic symplectic fourfolds.
Okay, so it's one more than the...
Yes, one more than K3. Okay, so we can do the following construction. Our X here is obtained as intersection of Grassmannian, some linear space, and a quadric. So you can look at the double cover of the linear section of the Grassmannian branched along X. So this is a double cover. And it turns out that this X tilde here, which has dimension 1 more, is a deformation of our varieties of dimension 1 more. Okay, so this turns out to be deformations. This is a standard construction. Deformation of GM varieties of dimension n+1. Well, except in the case where n is equal to 5, we get new GM varieties of dimension 6. Okay, so this is actually Mukai's classification that I mentioned at the beginning tells you that the varieties which have the numerical invariance, which I consider, are either of our type or these double covers. There are no other cases. Anyway, so once you have this and you know that it's a deformation, you see that you've changed the parity of the dimension of X. Okay? So you have a choice. You can, it means that in each dimension you have 2 period maps. Okay? One goes to A10 and the other one goes to this period domain D.
So the dimension of moduli is what?
Moduli of what? Well, it's 20 plus 2, 4, 5.
But it's increasing as you go to higher dimensions.
Too much for what?
For n equal 2, is it?
Yeah, the Torelli is not... No, so for n equals 2, it corresponds actually to these points which I avoided here, which I call YA equals 3, okay, which map actually to a divisor. They happen
Okay.
in dimension 19. So, that's the expected picture. Oh, there's something else that I need to mention. I'm actually still at point number 2 here. Well, it's a mixture of point number 2 and 3. Okay, where is the symplectic fourfold here? The symplectic fourfold was constructed by O'Grady. He constructed a canonical double cover of these of the EPW sextic, which is branched along the singular locus. So this is a surface. It's branched along a surface. So it's not a standard situation, but this is a singular. But the singularities are such that this double cover turns out to be smooth. And it's a smooth, irreducible holomorphic symplectic fourfold. So smoothness, actually, for smoothness, you need, again, to exclude the case, you need to assume that this, so this is true outside of a divisor. So this is true in general. So this is the this is a theorem of Grady. Okay, so now we have a picture. Some of it is conjectural, and some of it is proof. But I don't like the proof that we have at the moment. Okay, so it goes like this. So you have your moduli space of our varieties of dimension n. There's the map that takes the variety to the associated Lagrangian A. There's a period map that goes to a period domain here, which I'll call, I don't know if I need to give it a name. So this is the period map that corresponds to hot structures of K3 type. And there's a period map that goes to the moduli space of 10-dimensional abelian varieties. Okay? So these are the two period maps. So depending on the parity of n, you take either directly the period of x or the period of this, the double cover. Okay? So this first map here is the one that is there. I claim that there is a period map here which takes A to the period which I haven't defined, but the period of a smooth, this smooth fourfold. And this map, again, by Verbitsky theorem, is an open embedding. So, of course, we would like this diagram to commute. So this is the expected picture, is that this diagram should commute. So in particular, it would give you a complete description of this period map here. So thoroughly is not true, but this has been known for a long time because you can compute the differential of the period map, and you can see that it's not injective. And what about the relationship between these two here? Well, we expect that there should be a map like this. This map here is not injective. It should be 2 to 1. It is at least 2 to 1, but it should be exactly 2 to 1. And correspond to, there's a natural involution here. And it should correspond to, so this is much bigger, right? So this is an open embedding, but this should be, this is too big. There's a natural involution that comes from the construction of D as a quotient of some domain by an arithmetic subgroup. And so there's a natural involution here. There's a natural involution here too, which is the duality, which I probably won't have time to mention. Anyway, so this is what we expect, and what we have proved is that this is indeed this part here indeed commutes for n equals 4. So this is the analog of the Beauville-Donaghy property. In some sense, you need to find an isomorphism between this hot structure with intersection product and that one. With the Beauville-Bogomolov form. Okay, so you want these two to be isomorphic. The problem is that there is no, you see, in the Beauville-Donaghy situation, the variety you had here was just parameterized lines on X. So there was a natural map. Once you have a natural map, it's not too difficult to prove by monodromy arguments that it should be an isomorphism. But you need a map. And in this situation, it's not clear that we have the right map at the moment. Okay. Okay, so okay, I have a few minutes left, and I'll talk about the last point. Well, the one that will be the last, which is birationalities. So let me talk first about rationality of these varieties. So so again, I'll assume that n is at least 3, otherwise the rationality is easy to settle. So when n is equal to 3, it is known that most, let's say, a general x is not rational. This is proved, for example, in Beauville's thesis. Maybe it was known, no, maybe not. I don't know. Anyway, so how do you prove that? So x is not a conic bundle. It's intermediate. A general x, you cannot express its Jacobian as a prime variety, so it's difficult to analyze the singularities of its theta divisor, which is the main tool that we have for proving that something is not a Jacobian. Okay? If you want to prove that a principally polarized abelian variety is not a Jacobian, one way to do it is to prove that its theta divisor has a singular locus which is too small. Okay? So, but the way you do it is that you can degenerate x to, if you look at the situation where x acquires a node, then the intermediate Jacobian becomes a prim, and it's a prim. It's actually it is a yeah. I wanted to mention that. This is an example which was mentioned by Chelsov. It becomes a divisor of type 2,2 in P2 cross P2. Okay. Well, it's sort of there's a birationality with this. Anyway, so you can prove that its intermediate Jacobian is not a Jacobian of a curve. I'm being a bit sloppy here because x has a node, so this is not really an abelian variety anymore. But anyway, so this is the principle. And then, so we don't know that, so it is not rational. So we don't know that rationality is an open property or not, but we know that not being a Jacobian is open. So this sort of, this is true on a big open subset of the family of all these 3-4. Okay. So this is how you prove that a general X is not rational. I assume that, I think that people expect all of them to be irrational, but I don't think even a single example of an irrational one is known. Okay, when n is equal to 4, the situation is very similar to the situation for cubic fourfolds. So rational examples are known. And have been known for a long time. I think they were already, I found them already in a paper by Roth, like in the 40s. I don't remember the exact date. Rational examples are known. No smooth irrational example is known. So same situation as for cubic fourfolds. Actually, there's a some of these varieties are birational to some cubic fourfolds, so, which are not known to be rational. So. Anyway, so there's an intimate relationship between the two. And the last case, actually, I could also include n equals 6, which happen, these varieties are all double covers, but okay, let's stick to n is equal to 5. These are known to be all rational. And again, this is this is in the same. There are many constructions, but this is more or less in the same paper by Roth. Okay. So I still have 2 minutes, and the last thing I want to tell you is that it's sort of interesting. So often people think that there should be a relation between a rationality of a cubic fourfold and its period point. Okay. Well, here, what we can prove is that all, so let's say n is equal to 4, but this is true actually for all n, but for n is equal to 4, all the varieties in the same fiber of this map here are birationally isomorphic. So, theorem. All varieties in the same fiber of, let me give a name to this map, so it will be easier, of pi are birationally isomorphic. So for n is equal to 5, this is I mean, of course, it's a consequence of the fact that they're all rational. But when n is equal to 4, it means that rationality only depends on the period point. When n equals 3 also, but we sort of expect that they're never rational, so it's less interesting. Anyway, so of course maybe this problem is more difficult than finding irrational cubic fourfolds, but who knows, maybe not. And also maybe I should mention that as I said at the beginning, this period map here for cubic fourfolds has been compactified by Radu, and so O'Grady tried to do the same, sort of finding how to extend or not extend the period map. There's a natural GIT compactification here. There's a natural Bailey-Borel compactification there, and you can study whether this map extends or not. But it's really a mess. So. Okay, so I'll stop here.
Okay, questions or comments?
Could you explain this 2-to-1 map from G to 18 didn't follow the
This one here? Yeah. Well, so this is constructed as the a quotient of some domain by an arithmetic group, and so there's this group is of index 2 into another bigger group. So there's a natural involution here. And and O'Grady proved that if you take there's a natural notion here of duality, that if you take the dual here, it corresponds to performing this involution on that side. Okay, and so this one.
No.
This one.
Yeah.
So this one we don't know. I mean, you can compute the differential of this map. So, and they fit. I mean, the dimension of the fiber is as predicted. But you cannot exclude the case that there would be, for example, that this map would be more than 2-to-1.
Okay, thank you very much.